not record less?
Sorry?
Did it not record less then?
Oh, I don't know. Sometimes I forget to check, so you might want to remind you to check it once in a while. Once in a while. All right. So it is recording. Let's go ahead and get the class started. And we'll start with the homework assignment that was due about 30 seconds ago. So how was the homework assignment? Was it easy, hard, difficult?
Easy peasy.
Should be easy. I think because it resembles the example that I went through in class so much, and it has resemblance to the previous homework assignment as well, as far as the math part is concerned. So I think it really should not be a major time-consuming homework assignment, but we'll go ahead and do it anyway, just to make sure that we understand how to get this one done, because this is a good example of what might be in your test on Wednesday. What test again? It's your second midterm. It's about time because we are only about a month until the end of the semester. We are less than a month until the end of the semester. Okay, so let's go ahead and get the homework started. That's your homework assignment. And let me close off all the tabs that are not useful. Okay. All right. Zoom in a little bit. All right. Okay, any questions? Okay, do you guys have any questions? Okay, do you guys have any questions I can answer?
No, I just mean to show that there was a page with some more numbers on. I'm like, that's the answer.
Oh.
It's completely
Bogus?
Yeah.
Okay. All right, so we'll take a quick look at this homework assignment. Okay, it is recursive because on line 4, we can see that inside the definition of XYZ, it is invoking the very same subroutine that it is in. The only other invocation to XYZ is on line 11, which is in the main subroutine. Okay, but the mechanism of invoking a subroutine and the mechanism of returning a value from the subroutine really does not change, no matter where you do the invocation or the return. Okay, so the homework assignment and also what I use as sample programs in class, they are really designed to make it look confusing, but they're not supposed to be confusing because the mechanism has never changed since we introduced the mechanisms. Okay, so we'll take a look at the solution of this homework assignment and see why I claim that the mechanisms have never changed, even though the context may have changed depending on which program we're dealing with. All right, so here's the trace, and this one from my perspective will look a little bit ugly because I will need to scroll horizontally and vertically quite a few times just because my constraint on the screen is kind of more limited compared to what you probably experienced as you work on your homework assignment. All right, we need one column for comments because they are conditional statements, particularly the one on line 3, starting with an if. We have line number, the usual stuff. We do not have any global variables because in main, the references to x is referring to local variable x. It is declared on line 10 as a local variable. And in subroutine XYZ, x refers to the by-value parameter x. So x is never really a global variable. Okay? If there's one global variable x, it will not be used at all in this program because in all the context, x will be hidden. The global variable x will be hidden by the local definitions. So as far as we are concerned, the precondition really has nothing to say because there are no global variable to state anything about. We start execution on line 13, which is the first line outside of the definition of a subroutine. And to warm up, we just do the usual call without a return value. Without the return value, if you want to, you can also do a return info, except it's not really necessary because when we get back, it's the post statement anyway. So typically, we just kind of simplify the whole thing and say return line number is post. But this time, we do have one additional thing to do because main has a local variable. With a local variable, you have to allocate it while you invoke the subroutine. So we will allocate column D as local variable X, and as a local variable, from the caller's perspective, it always starts with an unknown value. Questions? No questions? All right. So now that we have set up column C and column D, it is time to continue execution in main, starting on line 11. On line 11, it is an assignment statement, but I can't do the assignment part because I have to evaluate the right-hand side first. But the right-hand side is not, I cannot evaluate it right away because it is the return value of an invocation of the subroutine. So this time I have to invoke XYZ, but because XYZ returns a value, I need to use return info instead. So the idea of using return info is we are going back to the same line. So I cannot use return line number and say we're going back to line 11, because if we go back to line 11, then we'll start the whole thing again. It becomes an infinite, it won't stop, okay? It's not exactly a loop, but it won't stop either. So we need to use return info so that we can separate the fact that we are going back to line 11 from the fact that a part of it would be done by the time we get back onto line 11. So the invocation itself is the one part that is replaced by a single question mark, so we have a placeholder for the return value, which in return will be used for the assignment operation. Now I'm trying to explain the rationale of all of this stuff here, because with understanding the rationale, I'm hoping that it will be easier to follow the actual mechanism. We need one more column here. Column F is also for the by value parameter X, and the value that we pass to parameter X is specified in the invoke statement itself, which is on line 11. We specify a value of 4 to start parameter X. Okay, so that sets up the two columns needed by XYZ. Well, this is the first invocation of XYZ. And then we continue execution on line 3 inside the subroutine. The first thing it wants to do is to say, okay, is X is greater than 0 true or false? Now when we refer to X, there are two X's here, but there's only one. We always refer to the one that is the rightmost. In this case, column F is the rightmost column that has a label of X. That's the one we are using. 4 is greater than 0 is true. Then we move on to the then branch, which is on line 4. Line 4 is that's really the big test of this homework assignment is line 4, because everything else should be fairly easy. Line 4, when you look at this, you have to break it down into components. Then you know what to do with this. Okay, it's a return statement, but I cannot do the return part because I don't know what value I'm returning. The reason why I don't know what value I'm returning is because the right-hand side is invoke blah, 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 plus X plus 1. I can figure out the plus X plus 1 part pretty easily, but I can't figure out what is the invoke part. So I have to do the invocation before I can evaluate the expression and then do the return. So that means I have to do the invoking again. Now remember what I said about, it doesn't matter whether you're invoking on line 11 or invoking on line 4, the mechanism is exactly the same. So in this case, we are going to replicate exactly the same process. We will allocate one column for return info so that we know what to do when we get back to line 4 in this case. So on line 4, we have the return part that is still being done, and the question mark is indicating or taking the place, is the placeholder of the return value, and then we just copy the rest of that line, which is plus X plus 1. We do not substitute the X with the actual value of X. We don't do any calculation. Okay, we just leave it the way it is and just say, okay, that's what we need to do when we get back. Is that clear? Is that okay? All right. Okay. And then the other thing we also have to do is to allocate another column for parameter X. Now that part may look a little bit confusing because when we are on line 4, we are using the value of X minus 1 to specify the value of X, which seems awfully confusing. But the X minus 1 on the left-hand side of the right arrow is referring to the X that we already know. The x on the right-hand side is referring to the x that we are trying to set up. So that will give you a clue of which column are we talking about regarding x on the left-hand side, and which column are we talking about concerning the x on the right-hand side. Okay, I can see a few conversations. Are there any questions that I can answer? Anything I can answer? No? Okay. How about over there? Is there anything I can answer? Okay, all right. Okay, if there are any questions, just kind of raise your hand, let me know, and I'll try my best to answer those questions. Okay, so in this case, x minus 1, the x of x minus 1 is the x that I already know, which is the x in the current invocation. The current invocation has x being column F, which has a value of 4. 4 minus is 3, and that is the value of the x that I'm setting up, which is the next invocation. So the 3 goes here. Are there any questions about this particular step? If I have to name 2 steps that are confusing in this particular sample program, this is one of them. The other one is what do we do when we return. That's the other part when it can be confusing. But if you follow the steps mechanically, I don't think it's going to be too bad. So are we doing okay so far with this step here? Okay, all right. So with this done, we will continue execution in the subroutine starting on the first part of the program. In other words, even though we are now on line 4, we just continue execution. When you invoke a subroutine, you always start from the beginning, which is on line 3 for this particular subroutine XYZ. So this is where it is going to be handy if I split the screen into 2 parts. So this way we can just kind of focus on which part we are in. So on line 3, once again, we ask the question, x is greater than 0 is, well, once again, we look up the rightmost column that has a label of x. Column H is now the rightmost column with a label of x. It has a value of 3. 3 is greater than 0 is true. So now we move on to line 4 again. And what do we do on line 4? The same thing that we always do when we invoke a subroutine. Okay? Because even though it is a return statement by itself, I cannot do the return part until I know what return value that new invocation of XYZ is going to return. So it's going to be the same setup here. For those of you who noticed the pattern, you can even do a copy and paste here because we have to set up a return info column and an x column. The only thing you have to change is the value of x. Because in this case, the current x, okay, the x of the current invocation has a value of 3. 3 minus 1 is 2, and then we use that 2 to set up the x of the next invocation, which is column J. But that's the only difference. So okay, so now we focus on the new invocation. Once we set up the 2 columns I and J, we continue execution in the subroutine. Yep, go ahead.
Why don't you replace the question mark with 3?
Why don't I replace the question mark with 3? Because the only time you replace a question mark with a value is when you execute a return statement. But we are not executing a return statement yet. We are still invoking until the end, which is going to be in 2 more invocations. Then we go back, then we start to execute return statements. So at this point, we have not executed a single return statement because the value that we are returning has an invocation, and we have not resolved the return value of that invocation yet.
But just to be clear, column H, I think it is saying that the value of the question mark will be 3.
You mean here?
Yeah, the column H.
That column H, this is column H.
Yeah.
This is the parameter. This is parameter x of the second invocation of XYZ.
Okay.
I'm not quite sure what you're asking, but let's go ahead and maybe ask it in a different way.
Well, because you got the value 3 by doing x minus 1 and the sign is x on line 4. And
Correct.
That's where the question mark was.
You mean this question mark?
Yeah, that was replacing the invoke XYZ parentheses x minus 1.
The invocation is replaced by a question mark. But the invocation that starts, column I and column J is going to specify a value of 2 for the parameter x of the next invocation.
Okay.
Is that okay or not? There are two concepts involved. The first one is the invocation itself is replaced by question mark because it's a placeholder for the return value. The second concept is passing parameters, which is which is this part here. So this part here is the parameter passing part, which is basically saying, okay, x is a parameter of xyz, which I'm calling from here. What value am I using to initialize x? Well, it is x minus 1, but the x of x minus 1 refers to the x of the current invocation, and the x on the right-hand side of the right arrow refers to the x of the next invocation, the invocation that I'm trying to set up. In other words, it's kind of like scaffolding. I'm standing on a platform that is already stable, and I'm trying to set up the scaffold to go one step higher. And the x on the right-hand side is the extension part that I cannot quite stand on yet. And then the x of the x minus 1 is the x that is already on the stable part of the scaffold where I'm standing on. Is that kind of okay?
Okay.
Maybe we should look at this like this way so we can actually see the scaffolding building up. Okay. All right. So we're going to do the same thing here on line 3. We keep asking the same question. X is greater than 0 is true because x refers to column J in this case. It's the rightmost column with a label of x. And then we go to line 4, and once again we'll do the lazy approach, copy and paste and then modify. So we copy, paste, and just modify this to a 1. Change the column a little bit so it doesn't take up too much space. And now we go into the new invocation. This is the third invocation of xyz. Starting on line 3 again, x is greater than 0 is true. We go to line 4, and then we do this one last time. Okay, copy and paste, and this time x has a value of 0. This is when we stop. So we do use up quite a bit of columns in this case, in this particular trace, but it's okay because it's just a spreadsheet. On line 3, x is greater than 0 is no longer true. It is now false. So if the condition of a conditional statement is false, we go to the else statement, which is on line 6. So we now go to line 6. This is the first time, okay, on row 20 of the trace, this is the first time in this particular program that we execute the return statement. We encountered the return statement, but this is the only time that we actually execute the return statement itself. Now, when you execute a return statement, what you do is you copy and paste the rightmost return info cell, and then you change the question mark to the value that you're returning. That's the only thing you need to do. You don't even evaluate, okay? Because, but this one, we're returning 0. So what does it look like? You copy, paste, change the question mark to the value that you're returning, and you're done. You don't ask, oh, but which x are we talking about? Are we talking about this x on column n, in which case we should evaluate the whole thing to 1, or are we talking about the x on column L, which is 1, then we have 0 plus 1 plus 1 plus 1. We don't answer that question. We just say, it's 0, replace it, and you're done. Okay? So once again, we are executing the statement on line 6. Okay, this is what we're executing. As a result of that, we copy and paste column M to over here, change the value, change the question mark to a 0, and we're done. That is the result of executing a return statement. Okay, so after the line 6, we get out of the conditional statement. We get to line 8. Line 8 is the end of the entire subroutine. It's got 2 things to do. One is to look up the rightmost return info so that we know where we are going back to and what else do we have to do when we get back. So according to column M, this is where we have to go back to. So the approach that I use in this class is I just copy and paste this entire thing to the line number columns. This way, it's really, really clear what we have to do when we get back there. The second thing we have to do when we get to the end of a subroutine is to end not the subroutine, but to end an invocation of the subroutine. Okay? So we ended the invocation of this subroutine, which means everything that we allocate for this invocation is now time to deallocate. Okay, we free up all that space so that this space can be reused if we need to. So we copy and paste the heading, and then we just use a font strikeout effect to indicate that we don't need it anymore. So now so column M and N are now gone. So by the time I get back onto line 4, because of this, we are now on line, let's see, okay. So we are now on line 4, and line 4 now looks like return 0 plus x plus x plus 1. So once again, this x refers to the column that has the label of x that is the rightmost one, and column L fits that description. So x is 1, now we have 1 plus 1 plus 1. It doesn't actually calculate a square, okay? This one does not do the same thing as the other one. So we're executing this statement. Okay, what do we do when we execute a return statement? It should be pretty boring by now because I have repeated it so many times. When we execute a return statement, we have, let's see.
Replace the question.
Okay, first of all, which column are we dealing with? It's the rightmost return info column, which in this case is column K. And the second thing we do is we copy and paste that cell, okay? But what if that cell already has a return in it? I don't care. That part is not important. What if it has a syntax error? I don't care. That part is not important. What if that cell does not make any sense? As long as it has a question mark, I don't care. Because the only thing I do is to replace the question mark with the value that I'm returning. I'm not even executing that statement, okay? It can be syntactically incorrect. The error would not happen here. It would happen somewhere. It should happen somewhere else. So in this case, I am executing, okay, let me point out which cell. I'm executing this statement, and as a result of that, I copy and paste and change this question mark to the value that I'm returning. And you can see how it can be confusing because the statement I'm executing has exactly the same format as the return info cell that is being modified. So that's why you have to remember line number is the one column that tells you what you're doing, and then all of the other things are just helping you keep track of the execution of the program. So x has a value of 1, 1 plus 1 plus 1 is 3. Okay, we replace the question mark with the value of 3, and we are done. So at this point, yes, these two cells do look pretty much the same thing, except for the value inside the parentheses. Don't let it bother you. Okay? Line number column is the only part that tells me what I'm doing. So after line 4, we get out of the then branch, we get out of the entire conditional statement, we get to line 8. So once again, we got the two usual things that we have to do, which is to copy and paste the return info cell down here. So this way, not only do we know which line to go back to, we also know what else we have to do on that line. The second thing we have to do is to deallocate the columns for this particular invocation. So we say, we go to here, right click, go to strike through, and now we are ready to execute line 4. But you have to remember the column K and column L are no longer around, they're not allocated anymore. So the current context will be column I and column J. We are now executing this statement. Okay, we are executing line 4, but we're executing this statement. It wants to do a return because now it is time to execute a return because we know what 3 is, we know what x is, we know what 1 is. So we can do the summation, and once we are done with the summation, we know what value we are returning. So in this case, we have to look up, okay, which x are we talking about? Well, let's find out which column has a label of x that is also the rightmost column. As it turns out, it is column J. Column J has a label of x and a value of 2. So now we have 3 plus 2 plus 2 plus 1. So that would be, what, 8? Okay? So we are returning a value of 8. When you execute a return statement to return a value of 8, you look up the rightmost return info cell, which is column I in this case. You copy and paste it. Replace the question mark with the value that we're returning, which is 8 in this case, and you're done. Okay, that's all that you have to do when you execute a return statement. So that means we are done with line 4 here. Then we move on to line 8 again. Line 8, once again, has got 2 things to do. It has to look up the return info cell, which is this one, copy and paste it, so we know where we're going back to and what else we have to do when we get back. And then once again, we have to deallocate the 2 columns that we allocated earlier for this invocation. So go through, strike through again to mark those as not used anymore. And now we continue execution on line 4. But once again, we also have to remember that column I and column J are now deallocated. So that means we have to shift the whole thing to column G and column H. We are now ready to execute line 4, which is return 8 plus x plus x plus 1. What is the value of x? Well, look at the rightmost column that has a label of x, which is column H. You scroll a little bit, it has a value of 3. So when we execute line 4, it is 8 plus 3 plus 3 plus 1, which is 15. Okay? So we're effectively executing return 15. When you execute return, you look up the rightmost return info cell, copy and paste it, change the question mark to the value that we're returning, which is 15 in this case, and you're done. Then we get out of the conditional statement, we get to line 8. Once again, this is line 8. It has got 2 things to do. Look up the rightmost return info cell, which is this one, copy and paste it over here. And then the next thing you have to do is to deallocate these 2 columns. Okay, copy and paste the labels and apply strike through. Now we are ready to execute line 4. Line 4 is now return 15 plus x plus x plus 1. The x refers to the rightmost column with a label of x, which is going to be column F. Column F has a value of 4, so it becomes 15 plus 4 plus 4 plus 1, which is 24. Okay. So return 24 means when you execute return 24, you copy and paste the return info cell, put it here, replace the question mark itself with the value that you're returning, which is 24 in this case, but you don't execute it, okay? Remember, you just replace the question mark, but the rest of that cell, you don't do anything about it, okay? You don't process it, you don't say, it doesn't make sense to me, you just don't do anything other than replacing the question mark. After we execute line 4, we get back onto line 8. Line 8, once again, we do those 2 things, which is, first of all, we look up the return info cell, copy and paste it. The second thing is to deallocate the 2 columns for this invocation and mark those as strike through. Now we execute line 11. When we execute line 11, as it is now, we already know what value we are using to change x, which is the value of 24, and then we just have to look up, okay, but what am I updating? Who's x? You look up the rightmost column with a label of x, which is column D in this case, because column E and F are now gone. So column D is the one that you're updating to a value of 24. And then after line 11, we get to line 12, which is the end of the main subroutine. So you look up the return line number in this case, which is post. Make a note of that, and then, whoops, I should be doing copy and paste. There we go. And then we have no use of these 2 columns anymore because the invocation of main is now done. So you copy and paste those, and copy and paste those 2, and apply strike through. Now we continue execution in post, which means we're all done. Are there any questions about this part? Yep.
I was just curious, when you were going to 8 before, I didn't put the return 8 plus x plus 1 in the comments column.
That's optional. Because in my notes, if you read the notes on Moodle, I did not use that either. But you have to effectively execute x8 plus x plus 1. So as long as you know what value is now resolved and what you need to do, that's fine. Yeah. But I do this in class though because it is extra clear, when we get back onto line 4, what else are we doing on line 4? But it's really the same thing as what you have already in the return info cell. Do we have any questions about this trace? Any concept questions? Because I think the mechanical part will come kind of naturally once you understand the concept, what a return statement really is doing. No questions? Go ahead.
So I think we have it.
All right. Are we ready to do another recursive subroutine trace? Because that's going to be in the exam on Wednesday, so I think doing one more may be helpful. Okay.
Yes.
All right. Do you guys remember Tower of Hanoi? Let's do that one. We won't be working with a high number because that's going to take what?
585 billion years.
Yes. Oh, you remember the exact number. I was just about to say about how it scales to the age of the sun, which I think is 100-something times.
127.
Good memory. How do you guys remember numbers like that? Okay, so we'll do a Tower of Hanoi, but with a small number. Okay. So the first thing I need to do is to write Tower of Hanoi as an algorithm. So we'll define sub. I'll just call it Hanoi. And it's going to require several parameters. So it depends on how we want to do this. I will number the posts as 1, 2, and 3. Okay. Let's see. Let me go switch back to my handy dandy notepad here. So we're going to have a Tower of Hanoi, and I'm going to use numbers to represent which post that I'm moving. So this is post number 1, this is post number 2, this is post number 3, and we'll use another number to indicate the number of disks that we want to move from post 1 to post 3. Okay? All right. It looks a little pixelated. I wonder why.
Your ink is not high enough resolution.
Yeah, but I didn't actually set anything. This is all done by default.
It's a joke. You can't get higher resolution.
This is weird. But it's clear enough. It's okay. It's just kind of bugs me a little bit. Okay. So getting back to here, we have Towers of Hanoi, and we have 3 parameters. So we have bival post A, okay, bival post B, and bival post C. Okay. And then we have the number of disks as well, which is bival N, and is the number of disks that we have to move. So A, B, and C is really I really should rename A, B, and C here. A is the from post, okay? This makes it very clear. This is the from post. B is the intermediate or the temporary post, TEMP post. And then C is the to post or the destination post. There we go. I think this way it's just a little bit better. We know which parameter has what purpose, okay? All right. The algorithm itself, is recursive, and with any type of recursive algorithm, the first thing you need to think is, when do I stop? If I am lazy, okay, what is the easiest way, what is the easiest problem that I can solve that I don't have to call the subroutine again? So it usually starts with a conditional statement, and in this case, most of the time it has to do with the number n, okay, or the size of an array, or something along that line. So when n is 0, obviously there's nothing to do. But when n is 1, there's also nothing to do. Because if you only have to move one disk, there's no way you can move it out of order, even if you move it directly. Okay, so we'll just do it that way. So we say if n is 1, then we'll just do this, okay? Now the following part here does not really do anything, okay? Because I'm just gonna move disk from post to post. It really doesn't do anything, it's, because we are not, it might display a message on the screen, or if you want a 3D rendering and whatnot, you can actually have a character moving and actually move the disk around. So I'll leave it to the art new media experts to do this part, okay? Well, how would you guys do it if you are to visualize a program of Tower of Hanoi?
Probably with the Y and X movements.
Okay.
I mean, it's still coordinates, it's still a grid system, if you
Yep.
think about it. So you're just moving disks from one grid point to another.
But you can animate the whole thing. Instead of have the disk disappearing from one post and reappearing in another post, you can actually have a motion to do it like this. Or even have an animation of someone actually moving it from
Or you
one
can make
post
the
to the
post
next.
tops connect to each other and it travels over halfway.
Ah.
Imagine making like a prisoner do it, like he has to do it as like his
That's
punishment or
sentence.
whatever.
Your sentence is
Sentence,
55
yep.
Tower of Hanoi.
I would imagine it would take a really long time if you're just using OpenGL or DirectX without any 3D editor or anything like that.
Oh, you mean to come up with the animation?
Yeah, just type in this dot here, this connects and makes a
Do you
quad or
want to be
triangle.
able to be, the entire motion be able to be seen by the human eye? Because that depends on how many frames the movement takes.
That's true. Yep.
It'd be much easier to do it in 2D animation, just use vector animation.
Yeah.
You could do that too. But I like the idea of having a UFO flying over one post. Use a tractor beam to move up the disk and move the other one and drop it down, and have an alien in the spaceship to go wave at the camera. Just random thought. Don't know why. And make it Dalek too.
Daleks don't weigh, they just exterminate.
Well, they only say exterminate because of the filter of the suit of that thing. We know that because of the last season of Doctor Who.
That's right.
Okay, but what if it's not
The easiest case, then we can just move one disk because n is greater than 1. Because if n is greater than 1, you have to preserve the order. You cannot just take the entire stack and move the entire thing. Well, all we need to know is we can still break it down into a smaller problem, okay? Because what we can do is we can invoke Hanoi again. Invoke Hanoi, okay? And this time we can move one disk viewer from the from post to the temp post, okay? So invoke Hanoi, and then we say the from post is still the from post. So my from post is the same from post of the next invocation. The temp post is different. I'm going to use my temp post to become the temp post of the next invocation, and then the destination is my temp post. So my temp post becomes the to post of the next invocation. But even as importantly, n is now one fewer than before. Okay, so I know this is a really, really long, sentence or long statement here, but it is kind of the concept is simple. The concept is simply saying, okay, let me switch back to the handy dandy whiteboard, and we'll bump up the exposure like a few notches. It still kind of annoys me that it's kind of pixelated. Does it look pixelated on yours, really? Yeah, it does.
Okay, I want to fix it because it just bugs me. Okay, maybe it has to do with this transform. So without the transform, it's definitely not there. Okay, we'll do a hand rotation instead, 180 degree rotation. And when we do it by hand, it doesn't pixelate. So, okay. All right. So what we're doing is we look at the same problem again. Okay, we have from. This is from. This is temp. I should have called it via, and this is to. Okay, and all we need to know is it is not a single disk that we're moving. We're moving multiple disks. With multiple disks, we're only concerned about the bottom disk and the pile on top. Okay, so we look at the problem as two pieces: the smaller problem, and then that one bigger disk at the bottom. Okay, so if this is the case, then we can solve the problem by first moving the entire upper pile through. So we're going to move from the from post to the temp post using the to post. So the end result after that is going to have the big disk still sitting here, but this entire smaller pile is going to end up here, and the to post will be empty. And then after this, we can now perform the last step, which is, oh, actually that's not the last step, it's the second last step. We move this disk here, which is at the bottom here, all the way to here. Okay, that's the second last step. The last step is to move this entire pile, which is on my temp post. Then I'll use the from post as the via in order to get to the to post. So I will move this entire pile, on top of this. So I'm going to draw one more picture just so that we don't confuse the two. Okay. So the last step is going to have the large disk here, and then the pile on top of that, which accomplishes the entire mission. So from here to here, from this stage to this stage, is recursion. Okay, because I have to use the recursive method in order to move that smaller pile from the from post to the temp post. From this step to this step is just moving one disk from the from post to the to post. There's no recursion with that step. The last step, once again, is recursive, because I'm moving the middle, the big pile in the middle post to the to post, which is the final destination. Okay, so this is the approach, and the coding of the algorithm is a little bit long, but it's really reflecting just that. Okay, and so this is the first recursion. Then we just move a single disk, which is the bottom one, which is the only one left from the from post. And then we will do kind of the same thing again. So I'm performing the last step, which is here. So we're moving n minus 1 disks from the temp post to the to post. Okay. So when we invoke Hanoi, we want to use the temp post of mine as the origin, as the from post. I want to specify the from post as the temp post, and then I want to use the to post to specify the to post. So to post specifies to post, and the number of disks once again is n minus 1. So n minus 1 specifies parameter n, just like that. And if n defines sub. So that's the entire subroutine. It looks a little bit lengthy, but the code it just looks nasty because of it being verbose. So let me do one more indentation here. Okay, and we have main here, sub, define sub, main, and we just want to say invoke Hanoi. We use 1 to specify from post. We use 2 to specify temp post, and then we use 3 to specify to post, and we want to move 3 disks. Let's see, 2 would be good. 3 would take longer. So 2 specifies the 1, and define sub, invoke main. That's our entire program. Okay. We just need to assign line numbers, and this time I think I want to zoom out a little bit so we can keep an eye on the entire program at all time. So that's just about right. Okay. All right. So this is the whole program. When we get to the nasty lines like 15, 9, and 11, we'll zoom into the actual algorithm, but then we'll kind of overlap the 2 windows, other ones. So we go to the other window, open up another sheet for the trace, and once again we need comments because there's a conditional statement. We need line number. There are no global variables, so pre has nothing to say about anything. We start execution on line 17, which is the first line outside of any subroutine definition. So we say in return line number is post, and we don't have any local variables to define in main. So now we are ready to go into main, which is line 15. Main itself is invoking Hanoi, so now we need to use another return line number. Remember, Hanoi does not return a value, so this way we are only using return line numbers. All right, so we start execution. When we get back, we want to go back to line 16, so that's our return line number. Now we have to specify the 4 parameters. The first one is from post, which is 1. If you guys don't mind, I'm just going to use F to represent from because we'll need a lot of columns, okay? And then we have, I'll use V for via, okay, which is the middle one. That's post number 2. And T for the to post, which is our destination. And then N initially is 2, so this is just the number of disks that I'm supposed to move. There we go. So now we set up all the columns for the first invocation to Hanoi, then we start execution inside Hanoi, which is on line 6. Line 6 doesn't do a whole lot of thing. It just wants to know, are we at the simplest case? The answer is no, but close. So now we go to line 9. Line 9 is going to invoke the subroutine again. It's recursive, but this time the return line number is going to be line 10 because we are on line 9 and there's nothing to return, so we don't continue execution on line 9 itself. There's nothing else to do. The from post is going to be the from post itself, which is 1. But the via is going to be post 3. Because it is using my to post to specify the temp post of the next invocation. And then the destination is going to be post 2 because the way I pass the parameters. N is going to be n minus 1. My current n is 2, so the new n is going to be a 1. Are we doing okay so far with how the columns are set up? All good? Okay. Then we continue execution on the first line of the subroutine that we're calling, which is line 6. And this time line 6 goes like, oh, how many disks are we moving? Is it 1? Ah, yes it is, okay? So let me just split the screen again so this way it's easier for us to see the parameters. So let's close, get this one over here, and, oh, that's too much. There we go. We want to show it like this. Okay, so this is the current situation. We have on line 6, and on line 6 we want to look at n. N is the rightmost column that has a label of n, which is column M. It has a value of 1. 1 is true, so now we just go to line 7. And as I said a little bit earlier, line 7 doesn't really do anything that we can trace in a trace like this because it's an actual motion. So I would just indicate that line 7 executes, but I cannot really draw a picture. Well, I don't want to draw a picture to represent what it's really doing. So we just say that line 7 executes, and that's the end of the conditional statement. We get to line 13. Line 13 is a return. We got 2 things to do. First, we make a note that we are continuing execution at line 10. So make a note here. And then we just say that, oh, this invocation has ended. We have no use of column I to M anymore. So we indicate that these columns are no longer used by using the strike through effect. Now we continue execution on line 10. But remember, columns I to M are now deallocated. So we have to remember to change back to column D to H to execute line 10. Line 10, once again, doesn't really do anything that I can trace, so I'll just say that line 10 executes, but there's nothing to really describe in the trace itself. And now we get to line 11. Line 11 is a recursive call. So we're going to reallocate the same columns over here. So we will reallocate, let me see what is the best way to show it. Click. We're just 1 column short. I'm going to make the screen a little bit wider. Okay, come on. Okay, so we're going to reallocate column I for line number, and then the rest will still be here, V, T, and N. Okay, but when you read the code, I am using my temp post to specify the from post, which means 2 is used to specify the from, so this is a 2. The via is going to be my from post, which is 1, and then the destination is the same, which is post number 3. N is n minus 1. The current n is column H, which has a value of 2. 2 minus 1 is 1. So this is how we set up the parameters of the next invocation. The invocation itself is on line 11, but the return line number is not 12, because in the conditional statement, we do not trace the end if. So the next line to execute is line 13. So as a result, return line number is line 13 in this case. Are there any questions about how we set up the columns for this particular invocation? Yes? No? So good? Okay? All right. So now that we have set up all the columns, we go back into the subroutine that we're invoking, starting at the beginning of the subroutine, which is line 6. Line 6 says, oh, n equals 1 is true again. So now we go to line 7, which is basically just moving, physically moving the disk, which cannot be logged in the trace here. Then we get out of the conditional statement, we get to line 13. Line 13, once again, just has to remember, where am I going back to? We're going from line 13 to line 13. It's okay, it's not a problem. Whatever the return line number says, I'm just going to put it here. Then once again, we are going to deallocate the 4 columns that we allocated for this invocation. So just copy and paste it here because it's already struck out. So now we continue execution on line 13. Line 13 is the end of a subroutine, so we do exactly the same thing, but this time return line number is line 16. So we make a note that we have to continue execution on line 16. Then once again, we have no use of these 5 columns anymore. So I'm just being lazy here to copy and paste. And now we continue execution on line 16. Line 16 is the end of the main subroutine, so we will do something similar, but not exactly the same. We look up the return line number. This time we have to go back to post, and then we have no use of this return line number column anymore. Mark it as deallocated. And now we continue execution at post. We are all done. And that's the end of this trace. So here comes the question. What if I make that n, the initial n in main, instead of 2, I make it 3? How would that impact the trace? You just have to say approximately. Okay, a few questions. It's going to add 2 lines to the trace because A is just 1 more. Or is it going to add, well, almost doubling the number of lines? It's going to double. So this is kind of like the reverse of binary search. I hope you still remember binary search. With binary search, when I double the size of the problem, it only adds 1 more comparison, which means the number of times I have to go through the iterations is the log of the size of the problem. With Tower of Hanoi, it is the opposite. The amount of time it takes to solve the problem is exponential to the size of the problem. You add 1 more disk, it doubles the amount of time it takes to solve the problem. So those 2 problems are kind of interesting in a way because they're opposites of each other. They're both recursive algorithms. One with binary search, it chops the problem in half with each step, and that's why you have a log, a log relationship. This one, on the other hand, you decrease the problem size by 1, but you have to do it twice. Okay, and that's why that's why the amount of time it takes is doubling every time you add 1 to the size of the problem. Are we doing okay so far with Tower of Hanoi? Yep, go ahead.
Could you show us the original code?
Okay.
I didn't get to write it down.
That's okay. You can take a picture if you want. I think that part is your job. I'm sorry. I just think that it really is your job to kind of go through this. I mean, you can just kind of write it here, but as you're writing it, you want to think about it. Okay.
Any other questions about Tower of Hanoi?
Is there gonna be anything related to Tower of Hanoi on the test, or is it just like the concepts?
I'm only using Tower of Hanoi to illustrate the recursive concept of you can call a subroutine inside a subroutine. But the trace of this algorithm is really no different from the trace of all the other algorithms.
Just using it as an example.
Yeah, I'm just using it as an example. Yeah. Question? No. All right. Any other questions that you can think of related to the exam on Wednesday? Because it's going to be on arrays, it's going to be on subroutines, okay? But I did say no mixture of the two, okay? So
Is there gonna be any by value or by reference arrays?
there won't be any by value or by reference of arrays. If anything, arrays can be global variables, so I might mix that in. So in the subroutine, I can access an array that is quote unquote global. So this way it's not being passed, so you don't have to understand the mechanism of passing an array. But since we already talked about array indexing, it's still going to be the same mechanism.
You said arrays, what else?
It's going to be arrays and subroutine calls. So subroutine calls would include invoke, return. It would also include all the parameters by value, by reference, and local variables. But most of those concepts are so related, they're not really like completely different concepts. I would say arrays and subroutines are kind of completely orthogonal. One cannot be used to imitate the other one. But then all the parameters and local variables, they fall into the same bin. Okay. All right. We also talked about the 4 combinations of passing by reference, and then use that parameter to pass by value in the 4 combinations. So you might want to kind of study that one too. That's going to be important. Yep.
For the program there, would it be more correct to pass by reference or by value?
You mean for Tower of Hanoi?
Yeah, for the tower.
But why would you, what are you going to pass?
Well, if we wanted to return those values as well.
Okay, but what are you going to return as a value? Because Tower of Hanoi, is about moving the disks around. So if anything is of value on line 7 and line 10, is what you actually do when you get to line 7 and line 10. So in a visualization program, line 7 and line 10 would actually be the time-consuming part because it will actually display the animation of a single disk being moved. But in the context of robotics, those 2 lines would correspond to the control code to use a robotic arm to pick up a disk on one post and actually put it into another post.
Its own subroutine.
It becomes its own huge subroutine in some cases, correct. But as far as we are concerned, since we only want to understand how recursion works, to us, it's like, okay, we just say that it's done and it's done.
Yeah, I was gonna say if the disks were numbered, you could store them in an array during that portion, but.
Yep. Or you can just log in, send it out to a file, so you can see the ordering of going from post this to this post to that post to that post and so on. Because you're only moving the top disk in any case. So you only need to remember, only need to know from which post to which post. It's always moving the top disk in that case. All right. Any other questions? Now, for those of you who want to get a visualization of Tower of Hanoi, there are plenty of choices on the internet. Okay, because I think it really is helpful if you want to take a look at the actual animation. And I know some of you are experts on animation and graphics design and stuff like that. And you can probably look at some of these and say, I can top that. Tower of Hanoi animation. Tower of Hanoi animation. This one is Flash based. Because mine is out of date already. That's my complaint.
Game instruction, choose the number of disks, start. There you go. And it even has explanations, solving the problem. Oh, it wants me to solve the problem. Okay, fine, we'll do it. Okay, remember we can only move one disk. So the idea is to move both of these into here, move the blue one all the way to over here. But I can only move one disk at a time. So in order to solve the problem of moving two disks from here to here, I first have to move the yellow disk to here, move this one to here, and then move this one back here. I have just solved the subproblem. Then I move the blue one all the way to the destination. Now the blue one is all done. Okay, it is just as good as not being there to begin with because it is the largest disk. It cannot be out of order no matter what I put on top of that. Okay, so my subproblem is now to move these two disks through this one to this destination. Okay, which involves moving this one first from here to here. Now I can move the red one from here to here, and then move the yellow one from here to here. So number of move required is 7, percent score is 100.
I always thought it was you can only put one post location at a time too.
Oh, can only be adjacent post? Yeah, I don't think that's a requirement of the original problem.
That's another temper.
If you have that extra restriction, I'm pretty sure that's gonna be well. Okay, first of all, if you have the extra restriction, I'm not even sure the problem is solvable.
It is.
It is? Okay.
It just takes a lot longer.
Okay, even longer. This is already long. All right, so this is one animation where I have to do it. I think there's an animation that actually has the program doing the animation for you. Ooh, look at that. Okay, so let's go back to 3 pegs only. We want to move 3 disks. Speed factor is 1, I guess, the higher the faster. And 3D effect, get solution, show solution. There we go. I guess the middle post is the destination in this case. There you go. All right. Yep.
We do one with a lot of discs to make it looks like to make it go really fast.
Speed factor.
Oh, bump up the speed.
Yeah, like 10.
Okay, 10 is got to be pretty fast already.
With a bunch of discs though.
Oh. Okay, there we go.
Now change the amount of discs to like
Remember, it's exponential. 4 is already going to take quite a bit longer. Okay, get solution, show solution. There you go.
Now 15.
You guys just want to run the
speed
clock
factor of
down.
25.
Yeah, but this is one of those things where the amount of time to execute is exponential, and it's not the worst. Okay, so when you have an algorithm, okay, I'm going to introduce a little bit of a concept, the big O concept, which is really just saying proportional to. Okay, so the execution time of tau of Hanoi is what we call big O of 2 to the power of n. In other words, the amount of time it takes to solve a problem is roughly proportional to 2 to the power of n, where n is the number of disks. And you might think this is a pretty bad problem because it means every single time you add one more disk, it's going to double the amount of time to solve the problem. But it's not really the worst, okay? Because I can think of at least one that is really common and is worse than this. It's n factorial. Because if you compare 2 to the power of n, each time you add 1 to n, it's only doubling, okay? Because the multiplier from the one before and the next one is just a factor of 2. This one is a factor of n itself. So when n is, let's say, 1,000, okay, to go from n minus 1 to n is 1,000-fold more time consuming instead of twice. Okay, so n factorial, even though it doesn't sound really bad, it is a lot worse than to the power of.
And there are intrinsic problems. There are problems where intrinsically it has an order of n factorial, or something times n to the factorial, which is worse. Okay. Did I talk about the traveling salesman problem? Okay, that is a classic problem where the time complexity is n factorial, but only on conventional deterministic machines. Okay. Did I explain what is NP? I think I did. No? I thought I did. Okay, NP complete it describes an entire class, an entire family of problems where the time complexity is this bad. Okay? But it has to do with the NP is actually kind of interesting because N stands for non-deterministic and P is polynomial. Now what does polynomial mean? Polynomial really means big O of n to the power of some constant k. That's P, polynomial. So how does traveling salesman problem, which is an NP complete problem, ends up with n factorial? It sounds kind of contradictory because on one hand, I say it is n to the power of some constant, can be to the third, can be to the fourth, can be to 100, okay? It is still polynomial time. It is not too bad compared to n factorial. So how do I relate polynomial time, which looks like this, to the actual complexity, which is n factorial? It has to do with the n here. N is non-deterministic, which means you have a magical computer where you can spin off a new core whenever you need a new core. Okay, so you know that most the i7 now has what, 8 cores? 8, I think. Okay. But okay, let's say it's 12. It's a constant number, right? It's not an undetermined number. Okay, it is a fixed number. This n basically means you have a magical processor where whenever you want to, you spin off a new core that is completely parallel to all of the other cores. Okay? With a magical processor like that, then it will take polynomial time to solve the problem.
I need that for rendering.
Yes. In which case, everything will become big O of probably n, probably 1,
Yeah.
or it would be n in terms of the number of objects you need to render, assuming you're doing ray tracing. Yes, that would be awesome.
I'll take that. Thank you.
In a way, you do. Okay, I know this is a really a sidetrack, but before I go on the sidetrack, is that okay? I mean, conceptually, do you guys kind of understand the idea of what is NP, what the N really stands for? Okay. So it's a theoretical kind of processor. Then you can get the really good time complexity. But with conventional processors, where it's all sequential or there's a fixed number of cores, then you're stuck with something that is really bad. Okay. Now getting back to the infinite number of cores, not quite infinite, but how are GPUs or graphical processing units? How are they structured?
Micro processor cores, CUDA cores, if you're using NVIDIA cards. And they're harvested, they're not harvested, they're harnessed for using, or actually some 3D scanning and 3D modeling applications already for rendering.
Or cracking, encryption, that sort of thing. Okay. So with a GPU, what happens is they are.
Making big currency.
What is the number of a cell or number of processors in the current architectures? Well, we'll take a look at NVIDIA.
Yeah, it's NVIDIA.
Okay, and introduction to blah blah blah. Okay, computing, stream, processing. I guess we are gonna skip
I
to.
can look at my video for
Or better yet, another way to do it is to go to Newegg.
CUDA cores.
We go to Newegg, we go to components, go to graphics cards,
My personal graphics card is 1600.
16?
1600.
1600, that sounds about right.
1664 per
Okay.
core.
Okay, so we look into graphics card, we go to desktop,
I've got 2 of them.
and then we go for the most expensive part because they tend to be
Oh, that's a 970. That's actually what I'm running. I'm running 2 of them.
this one.
Yeah.
Okay. So we'll take a look at this.
I was going to say, I don't think the the professional ones have more cores.
Okay, we need to click this away. All right, there we go. All right. So does it say anything here
It has it on the spec sheet.
on the spec sheet? Specifications.
There it is.
Here we go. So it has got 1,664 what we call CUDA cores. So these things are all kind of doing processing at the same time. Depending on what type of rendering you want to do, if you're doing ray tracing, you can literally speed up the whole thing. The more processors you have, then the faster you can speed up the process of ray tracing. So that's why the number of cores is a big deal when it comes to rendering using a graphics card. But these cores are all they're not general purpose. It's not like your Intel processor. You cannot just run any software on it. You can only run certain types of algorithms on these things, and they are, architecturally speaking, they're streamlined for the processing that is needed for graphics stuff. Okay, so it's not really for general processing. Is it true or not that they all have to execute instructions of the same type at the same time, or are they asynchronous? They are asynchronous? Okay. So, but you do have 1,000 of these things going on. So if you have a problem where you can divide a big problem into equal pieces, and the equal pieces do not interact with each other, with these processors, you can actually speed it up by the factor of the number of processors, which is great. Sorry?
I've got 2 of those cards in my box.
You get 2 of those boxes in your computer. So you have 3,300 something CUDA cores, all operating at 1.something gigahertz at the same time. Now, the next question now is, well, an i7 processor by itself is about 90 to 120 watt of power dissipation. It has 8 cores inside, okay? Or the latest version has 8 cores. So with 1,000 cores like this, isn't heat going to be a big problem?
Probably why it has 3 fans on it.
Well, it's got 3 fans on it, but it doesn't scale the same way either. In other words, one Intel i7 core consumes far more power compared to one core of a graphics card. And that's because it's what we call a RISC architecture as opposed to a CISP architecture. They don't waste a lot of silicon doing silly stuff like backward compatibility. Okay, how many people understood what I just said? A few. Okay, very good. That's okay. I'm going to explain those. We have a few minutes left. Unless you guys have some burning question about the topics that will be in the second exam, we'll kind of digress a little bit. RISC stands for Reduced Instruction Set Computer. Okay, you don't have to write it down. It's not going to be in the quiz or the final exam. CISC is CISC, which stands for Complex Instruction Set Computer. Okay, so it's easy to remember. One is reduced, the other one is complex. They're opposites of each other. The Intel processors, or what we understand as quote-unquote the Intel/AMD processor, like the i7, i5, i3, the whole family, they all belong to this CISC family, which execute instructions really fast. Okay, we're talking about 2-3 gigahertz, and they have multiple cores and all kinds of ways to optimize the performance. But it depends on how you look at things, okay? There are several ways to measure quote-unquote performance of a computer process. The first one, typically they're called MIPS which stands for million instructions per second, okay? In other words, you're measuring how much computation can be done per second, which sounds like a really good way to measure the performance of a processor. It is almost the same thing as miles per hour for cars. You're measuring the top speed of a particular car. Okay, let's just say with a Corvette, the maximum speed is, I don't know, 220 miles per hour. Okay, and with my Honda Civic Hybrid 2005, vintage, I'll be lucky to hit 85. Okay, so when you look at those cars from those 2 perspectives, you will say, Tack, your Honda Civic Hybrid is not really exactly high performing. Okay, fine. But there's another way to look at things. The other one is called
I guess you can kind of look at it like this. It's million instructions per joule, okay, which is a measurement of energy. Okay, 1 joule is the same thing as 1 watt second, or there are a few other ways to define it as well, but it's a measurement of energy, okay, which is approximately miles per gallon. Okay, it measures the efficiency. So in that case, I would say my hybrid Civic is going to win that particular competition hands down compared to a Corvette. The Corvette can be on 6th gear or 7th gear. I don't care which gear. I will still be winning hands down, especially when we're idling at a stoplight, because my engine won't even be on. It's just it will just turn itself off, when I'm not moving. Okay. So there are these two kind of measurements in processors as well. These are for cars. These are for processors. So you would think, but for processors, why do we care about energy efficiency? That's kind of the thing that you think about. I don't want to stop at a gas station every 2 days, as opposed to, if I drive a Prius, I can stop at a gas station every month. Okay. So why do we care about energy efficiency? It's not for saving money, okay, because your electrical bill is not that much. It has to do with heat dissipation. Because with a car, most energy, trust me, is actually converting into mechanical energy, okay? So the chemical energy stored in gasoline is mostly converted into mechanical energy. Modern day internal combustion engines are extremely efficient, okay? So they convert like 70, 80% of the energy, not into heat, but into motion, okay? With computers, it's the exact opposite. You pump 120 watts into a computer, almost all 120 watts turn into heat. Okay? So what that means is if with a processor that is high on miles per hour but low on miles per gallon, your biggest problem is not paying at the gas pump. Your biggest problem is how big of a radiator can you make so that you can actually cool down the engine sufficiently, so the whole thing doesn't melt down and kill itself. Okay? Now, that's a problem with your own processor, with your own game console and stuff like that. I think the early generations of not PlayStations, but Xboxes. The first generation of Xboxes has a notorious problem of not having sufficient heat sinking. Now when we're talking about game PCs or PCs that are geared for gaming, we have more of these issues, okay? And that's why people have water cooling and stuff like that. Now, if you think about that, okay, how many of those full game configuration PCs are you going to run at the same time in the same household, in the same room? 2, 3, maybe, okay? What about the data centers? What about data centers that Google needs to run? Okay, you have farms of servers, right? And they try to pack in as many computers as possible. It's not a problem of space. It's not a problem of power supply. It's a problem of heat extraction. Because when the density of server is that high, this unit becomes more important than this unit here. In other words, they would much rather have 200 little Honda Civic hybrids running around than a few Corvettes or a few big trucks running around, because they cannot extract the heat when the trucks are running, but they can more manageably deal with it when they are more efficient. So that's why in server farms, the lean is completely on risk these days. Now that shift, it's not always like this. Before, I would say in the 90s even, it always is CISC, and they always emphasize on this particular number. But past the 90s into the 2000s, then they start to run into the heat extraction problem. That became the threshold of how many processors you can fit within the same space. So the shift is slowly but gradually shifting over from CISC to RISC, and we are now measuring from mids per second, a million instructions per second, to per joules. Okay, how much processing can I do out of 1 unit of energy? So this is just a little sidetrack, because we were kind of on that topic.
And getting back to the original topic here, I know we are running out of time. Okay, the GPUs are great in this term. Okay, in terms of how much processing they can do on a per energy unit of energy basis, they are the best. They would top the i7 processor, hands down. It's kind of like a Honda hybrid. Well, it's like a Prius versus a truck with all those jacked up suspension and a tire of a Boeing 747. The monster trucks. So you kind of imagine it's a monster truck versus a moped. That's what we are dealing with here. The i7 processor has 1 versus 1 CUDA core. Okay. I just want to kind of let you know about these things, so next time you go buy your computer, you know how to read the specs better. So there'll be something you can take out of this class other than your grade and the basic stuff. Hey, when you go buy a new computer, you can still use something that you learned from this class. All right, I'll see you guys on Wednesday. So go study. Don't forget to study a little bit.